And in this topic, in this lecture, we will present seismic site amplification maps of Reclamation Island in Hong Kong, presented by Khaled Ibrahim Muhammad Ismail. I'm a PhD student and teaching assistant at Civil Engineering and Environmental Engineering Department at Hong Kong University of Science and Technology. This is the table of content for our lecture. Firstly, we will discuss the background, motivations, and objectives for our study. Second, geological condition and geotechnical characteristics at the proposed artificial island, Reclamation Island in Hong Kong. The third, dynamic soil properties of different soil types. The four items, the uniform hazard spectrum in Hong Kong and how we will choose the earthquake scenarios for our analysis. 5, development of design spectral acceleration for artificial island. C means we will see this later that we have 3 artificial islands and our study will focus on this island. 6, seismic hazard maps of island C based on 1D site response analysis. Finally, conclusions and future recommendations. First, background, motivation, and objectives. Actually, Hong Kong Vision 2023 Plus highlights the urgent need to address the significant housing shortage in Hong Kong. Limited land availability requires innovative solutions with artificial islands like proposed here. This is at the central water in Hong Kong, and this is just the sea now. We don't have these 3 proposed artificial islands, and we have already 3 small existing islands, Kuyushu and Bengshu and Sunshine Island, surrounding the proposed artificial island. And for seismic consideration for artificial island development, the problem is Hong Kong, the first thing, the Hong Kong is classified as having moderate to low seismic risk. This is almost safe here in Hong Kong. The most concern related to wind and typhoons, but the absence of a comprehensive seismic design code here in Hong Kong, because the building here in Hong Kong don't be designed be related to seismic, just for wind and typhoon. There is no seismic code in Hong Kong, but we need to create a seismic code, especially for special sites like artificial island. The unique geotechnical properties of reclaimed island, and particularly for the soft marine, underneath of these 3 islands, there are a thick marine deposit that's very soft clay and has a different dynamic properties, and we need to check even if the seismic input motion will not be very high, how is this soil can amplify the input seismic motion. So our objectives, the first objective is we will perform a one-side response analysis conducted to the model ground motion at the proposed site. And this approach provides site-specific amplification factors for various ground motion parameters and developing site-specific design guidelines for the structural and geotechnical engineers. And finally, we can get the seismic hazard site amplification map for 2 cases before and after reclamation, and also propose design response spectrum at Reclamation Island. The second, geological condition and geotechnical characteristics. Firstly, here we will discuss a little bit about literature geological condition at artificial island here at the central water of Hong Kong. And we can see this is this work already done by Leo et al. 2022 based on 3D geological modeling and management system at East Lantou Reclamation Site. This site called in the government Future Vision East Lantou Reclamation Site. This is the Lantou Island, okay? And this is the sea. And here we will build the new proposed artificial island. As we see here in the 3D geological model, we have 5 types of soil: subsurface soil, fill, peat deposit, marine deposit, stony deposit, and alluvium. This alluvium consists clay, silt, sand, and there are from 1 to 5 to 1 to 6 grades of rock. The weathered rock from the grade 6 to grade 4, or grade 4 to grade 6, and this one is the moderately and slightly and fresh rock, moderately decomposed and slightly decomposed and fresh rock, and we considered our rock head at the top of this rock type. Okay. And we can see here the surface for each soil type. This is the surface of felt surface, the end of the felt, and the surface of the end of the marine deposit, and finally the surface of the alluvium, and then the rock, the weathered rocks surfaces. And we can, from this, we can see the complexity of the non-homogeneous of the surface for each soil type. From this, we can take some, because our proposed will be here, and we can take some cross sections inside the 3D and see how is the cross section looks like. Here we have two cross section, Y1 and Y2, showing 3 geological zones, like we see here: island, shore, and sea. Island means this we are close to the existing island, like here and here in section 1. And we can see here, this is the rock type, the best rock. And we can see this is the rock head, called the rock head. So it has very shallow or on the surface. And when we will go inside the sea, we can see the variation of the depths of this rock uh, till the central of the sea. Here. Okay, we can see here the depths of the subsurface soil increase, and we can see the layering of the soil from rock grade 3 to 1, and then rock grade 4, 5, 6, and then the beach deposit and marine deposit, and finally with fill. This two cross section can show how deep the subsurface condition here, till maybe 80-meter thick below the seabed level here. Okay. And also we can see the changes of the rock head. This is very important in the seismic, the rock head level, because this red color consider the rock head for the fresh and slightly and moderately decomposed rock. And if we will start our analysis, we will put out input motion here based on the outcrop motion at the surface, and then the propagation will done at this direction, and then we will get the influence of this soil types and the dynamic properties of this soil types on the seismic amplification. Here there are 3 types, 3 maps from also the same paper, showing the seabed level, the top surface, grade 5 rock head, weathered rock head, the weathered rock and the rock head level. And if we will plot our 3 proposed island, we can see the seabed level. This means the elevation of the borehole, or the elevation of the sea bed. It changes from -4 to -12 NPD. NPD is the mean sea level in Hong Kong. Okay, it's called the datum here in Hong Kong, and we can see that there is a variation in the seabed level. If we consider Island Sea, we can see it's between -8 to -12, and also for the top surface of grade 5 rock, weathered rock, it varies from -10 to -50. And finally, the rock head level has a significant variation between -10 to -80 meters. And in our analysis, we will see the effect of this rock head level and the variation of the also of the seabed level, because what we need to reclaim this island, so we need to fill the seabed level till plus 7 meter, almost. Here in Hong Kong, plus 7 meter above the seabed level. This is the platform that we will build the buildings on after reclamation. Okay, so we can see minus 12 plus 7, almost 20 meter fill. You need to fill the area below the sea level and also plus 7 after the seabed level. Okay, here is our work. Here, after I collected maybe more than 400 number of boreholes at the site, this data, I need to show you that this one based on all data, and this data we don't have too much borehole here, and they depended on the interpolation between the old borehole that's spar a lot, and also we have a limitation here in this date. We have a limitation in the number of borehole in the site. But in 2023, when I searched on the geotechnical information website of Hong Kong, I found that the government already did a lot of geotechnical investigation work here. So I collected the new data, especially in the island sea, because the government decided to start with this island. And I collected all of the data inside this island and are surrounding the island. But most of this it's not boreholes. Some of them boreholes, some of them just like fibro core, just maybe till depth 15 meter. But the data here almost reached to the rock head. We can see here some of the borehole, some of the borehole logs here. We can see this is till 15 meter depth, 60, 40, and 40 meter from 40 to 60 meter deep. And we can see the variation, the thickness of the fill and marine, and also all types of alluvium, clay or silt or sand. And after that, the weathered rock and then the fresh rock will be appeared. Like see here, 5 soil types, fill, marine. It's almost the same as the literature geological features done before by Leo et al. 2022. There are 5 soil types, fill, marine, Australian deposits, and alluvium, clay, silt, and sand, and also residual soil, and 4 weathered rock based on CD, granite. This is granite and rhyolite. It is the rock types in one of the most famous rock types in Hong Kong, the granite and the rhyolite. Okay, with the different weathering. C means completely decomposed. This is the weaker soil type. H means highly decomposed, the grade number 4. Moderately decomposed, grade number 3. Slightly decomposed, grade number 2. Okay, so this is from weak to strong rock. And we can see also the topographic of the existing 3 island. It reached to 62 meter elevation. In this map, we can see this blue color means the seabed level based on the data of the borehole, the new borehole. The seabed reached to minus 20 in this zone, but almost is minus 50 at the island sea. Okay, and it varies from minus 5 to minus 50 meter. Continue geotechnical characteristics of island sea. So now we know that we just consider this island because we have a lot of geotechnical investigation report here, and we can decide we can study it accurately. And we based on the collecting data, I created these 2 maps related to the island sea rock head level and also the thickness of the marine deposit in this island based on the collected data. And we can see on the left side the rock head map. It varies from minus 10 to more than minus 70, minus 75 or 74 meter. This means this part of the island has the deepest rock head, and this part has the shallowest rock head. Okay, and we can see the rock head levels varies from minus 20 to minus 88 MBD. And related to the marine deposit, the very soft material here in the site, we can see it varies from 0 here. That's mean in this location of island C, we don't have marine, and for but almost, meaning almost the area, almost of the island area already contains a marine deposit and reach to 36 meters here on the southeast part, and also here we have 28 meter. But in this zone, it's like this. Here means the rock head is shallow, and at the same time we don't have too much thickness of the marine deposit. And finally, the maximum thickness is 36 meter, and at higher rock head level is not exist, like I said. And I collected the data. This is the data from papers in Hong Kong related to the unit weight, because I need this data uh, to get the shear modulus after we will determine the shear wave velocity. So I put them here for residual soil. It's like 80.64 kilonewton per meter cubic. And for all others, the soil type that we will use in this analysis, we will use these values for the unit weight. And here also I plotted the two others map related to the soil profile. Soil profile means from the seabed level till the rock head. Okay, and we have these two maps. This is the first one before reclamation, the second after reclamation, and we can see the variation of the soil profile. It's logic to find here is almost the most thick profile because we have the deepest rock head here. Also here we don't have very deep rock head, so the soil thick ranges from 10 meter till maybe 70 meter almost. And after reclamation, this will be increased because we will fill the island till plus 7 meter above the sea level. So here the minimum is 20 meter and the maximum is 90 meter deep here, the thickness of the soil profile. We will go to the dynamic soil properties of different soil type in our region. Firstly, I did some regression analysis for the standard penetration test for 4 types of soil, but for marine and estuarian deposit, these two are clay. This is estuarian deposit here in Hong Kong. It's like the normal clay, okay? It's not marine clay, but marine deposit it is called marine because it's on the sea. Okay, so I plotted this regression based on non-constant variance regression to see the scattering data and see the variation of the SPT depths with depths, SPT value with the SPT depths for each soil type. Here is alluvium sand, alluvium silt, alluvium clay. Here is CDG because we don't have any SPT value for stronger like highly decomposed or moderately and slightly decomposed rock. So here this is a completely decomposed granite grade 5, and this is too related to the marine deposit and ED, and we can see the mean relation cannot consider or represent the data because we have two scattered data above and below the mean. So if we need to use this, what the benefit of this, if you need to use the mean, we will not consider this and this and this and this. But if we will not, if you need to take the uncertainty into our consideration for design, we can model and run 5 types, 5 models. The first one is the mean data regression, and then the second is the mean plus or minus 0.5 standard deviation of the data, and the last one plus or minus full standard deviation. Okay, and in this trend, we will see that we take the uncertainty, and the designer can decide if he want to take the mean or mean plus standard, mean minus, or mean plus or minus. This is 0.5 standard, this is full standard deviation. I have a question if the audience can answer me. Which one of them is more conservative, more critical to consider? If anyone has the answer, please raise your hand. No? No one? Open the mic and answer if you have answer. All, uh, all of the audience hear me?
Yes, we
Hello?
can hear you. Yeah,
Okay. I will continue. So the answer of my question, none of them. Why none of them? Because now we study earthquake, okay? It's very, very complex. So we don't know about the input motion. So maybe this is critical. If the property or of the, if the frequency content of the earthquake maybe match with this, we don't know, okay? So none of them is critical. If we need to consider all of them, you need to consider all of them and see the result and take the critical result for design, okay? And after this, from the literature in Hong Kong, I got the relationship between the shear wave velocity and SPT based on field measurements in one of the area here in the north area of Hong Kong called Tumman area. And this published by Patrick et al. 2012. And he uh, finally gave us this the relationship for the CDG and the CDS and alluvium and clay and fill. And also here he gave me this clay for the marine, but I didn't take this because I didn't trust this equation here related to the marine. And I searched in the literature to find another one, not here, but yeah, I used another one for marine, for another, yeah, I used this, yes, because this related to SPT. But in my research, I divided the soil type for some soil type not related to all of them related to SPT. And also here in the Hong Kong, the government found that the SPT not represent because when I searched on a lot of Hong Kong reports, soil reports, I found many of SPT for marine like 120, 120, just 1, 2, or 0. And the government decided to move to the venture test in the site to determine and to get the unbreached strength for the marine and estuarine deposit. And based on this equation, I get the VS for the two clay layers for the marine and deposit. And just I need the overburden effective earth pressure, vertical stresses and water content, and just put the SU based on the site results and get the VS for each point of the SU. And here I can apply this for each SPT to get the VS. So the VS for marine will be rely on the undrained shear strengths, and for other types will rely on the SPT, and will be the VS for the marine and Asturian will be depend on the effective vertical stress and also moisture content. And based on Young et al. 2001, also in Hong Kong, I take this 68% for marine deposit in Hong Kong. Now, for after reclamation, this we can use this for before reclamation, okay? But for after reclamation, I need to get a VS and I need to know how the vertical effective stresses will affect the VS. So I plotted this for different soil types in the site for alluvium clay, alluvium sand, and for Styrian deposit, ED means Styrian deposit, and CDG. And I found like here you can consider this equation to get the VS after reclamation if the effect because the effective vertical stress will be increased. And this is good because R squared is 0.55. This equation can represent a little bit the data, but here the R squared is zero point 0.2, but I didn't have too much choice, so this is one of the drawbacks. I need to get the VS in the higher vertical effective stresses. For this, I didn't change the VS because it's almost constant if we see the scattering. And for this, I use this equation for the CDG. And for marine, I searched about any research related to consolidation of marine in Hong Kong, but I didn't find any of experimental data that I can rely on. So I used the Macau marine clay published by Howe and Locke at 2008. They did a lot of consolidation and get a variation of VS versus the vertical effective stress for anisotropic specimens. And this is the result of the experimental, and then I just get the factor and the keynote 0.75 for the at-rest because my case is at-rest, and just get the coefficient, and then I just interpolated the curve here to get the variation between VS and effective vertical stresses, and I use this and I plotted the points here, and I get this nonlinear relationship between VS and vertical effective stresses to get VS after reclamation and after fully consolidation of marine clay. Okay. Here, we need to know the first thing after we will get the VS, we can plot the profile for VS for all of the representative holes. This is one of them for before and after reclamation, like we see here. We have two profiles, this one before and this one after. This is alluvium sand. As I said, I didn't change the VS after reclamation, but others that you can see here, the marine, this is the marine, the orange color, okay? This is the marine, and how about this? This is the sandy filled soil will be filled in the sea, and we considered the dry and saturated sand VS like 190 meter per second, and 170 based on published published paper here in Hong Kong. And also we consider the unit weight for the dry and saturated fill sand 60 and 80.6 kilonewton per cubic meter. And here, after we will get VS, and we can now classification the site based on, we have two methods to classify our site based on VS30, the most famous things. But in Eurocode, I maybe 1 month or 2 months ago, I found one post on LinkedIn that Eurocode will cancel this. Also, 2 or 3 years ago, me and my supervisor didn't trust on this because VS30 means the average wave velocity till 3 meters, just 3 meter thick of soil, and maybe the rock head may be deeper, like our case. So here is the previous published Hong Kong classification group 1, 2, 3, 4. This new group I created based on my data because now we have a very thick soil layer. So I created this new group. We can see here the interval for VS30, 500 to 750, 320 to 500 from group 1 to group 4. And here, based on the small strain side period, the Papin 2012, this guy, he proposed this classification till group 4 based on the T site. But I can just say something here. He based on T site based on what? T site here for the Papin based on till the SPT number 100. If you will find any SPT number 100, just stop and consider this is the rock level, and just consider all of the layer above this, including the VS and layer thickness, okay, and get the side period. But in my analysis, in my site classification, I didn't use this. I get the T site till the rock head, not till the SPT 100. I have the rock head level, this is the surface level of the fresh or slightly or moderately decomposed rock, and then I calculated the T site above this level. And for reclamation site, T site becomes longer than 1 second, so I consider a new group from 1 to 1.5 second to capture our site. Has been proposed to cover this. Uh, and also, this one is close to typical residential building here in Hong Kong, 60-meter height, because here in Hong Kong we have a lot of high-rise building for housing. Uh, and we will see in the next the two maps for the classification site based on VS30 for before reclamation and after reclamation, and we can see the change based on the VS30. And also here we can see here this area improved from, because RC group 5, it is the weaker site classification related to the more thick of the marine and alluvium also and estuarine. And we can see just this area that has a shallow rockhead. It's one borehole group one. Group one is the stiff site, and then this is the group 4, and this is the group 5. RS mean here reclamation site. I just put it like this. Okay, and now we can see the difference between this classification and this. Here the T site before, here the T site after. We can see here is more conservative. And this time it is weaker than no, not more conservative here. It's maybe more accurate, because the T site based on two things, not just on BS, and also the thickness of the soil, and also based on the deeper soil profile. Okay, and here also for the after, we can see here some location be worse, not better, related to what? Because here the soil profile increase due to the fill sand, maybe till 20-meter thick. So the T site becomes longer, not shorter. Okay. So the site class moved to RS group 5. Okay. And here we 2 to 2 perform, because we will perform equivalent and nonlinear site response analysis. We need the dynamic probabilities for the all of soil types. So here I can show some of them based on the published data by Papin and also by Wang 2000 at reclamation site in Chung Kwan O here in Hong Kong. And I plotted this blue and brown. This is for the two model by Wong 2004, based on the resonant column test and dynamic triaxial test for marine deposit here in Hong Kong. And I plotted them with the international published model like EPRI 93 for PI 110 and PI 30. And finally, we consider this because this one for marine, because this researcher recommended to use this model for marine, and we can see the closest one is this one. If you need to use the international publish, not just the data we have, we can consider EPRI 93 at PI equal to 30 plus this index alluvium clay, and also that the damping ratio versus shear strain that I found in the literature. I collected all of the data. This is the old paper, and I brought them together and compare with this. This is the model proposed by Wang and the other for Sutek and Dobry for PI 15 and PI 30. And here we can see which one is better. Maybe this one also for PI 30 is better. And for other types, also for the alluvium silt sand and weathered rock, I collected the data here in Hong Kong to get the the modulus reduction curve between the G over G max and versus shear strain for different soil type and also for weathered rock. But for damping, I didn't find any relation or any model, so I just used Campbell for rock 1972. And now before we run the analysis, we need our input. Our input is the earthquake. So we need here we choose our data, our input data 11 because in ASCE 2022, they recommended to use minimum 11 earthquakes to get the spectrum matched with your site. So here, this is based on probabilistic seismic hydro analysis carried out by Papin at 2015 in Hong Kong. He proposed finally three classes or three design levels of earthquake at 2% probability of exceedance in 50 years, 10%, 63%, 10% it's almost the design, 2% is the maximum considered earthquake. So I just in this presentation will show the 10% probability of exceedance in 50 years related to design level. And this, I just converted to this in Excel. And then I plotted the 11 selected earthquake to see that the median of this 11 earthquake almost match the response in the short and medium and long period. And this is the earthquake that will be used in our design, and the median of the result will be presented. The first of our output is the development of design spectral acceleration for artificial island C. We can see here because we have three groups. We have group 3, group 4, group 5. But if one asks me how about this is related to after reclamation. I didn't consider the before because it's nothing. We will not use the before case. I just show the before case to show you the difference between before and after cases. But finally, after we will fill the reclaimed sandy soil, we need the spectral acceleration on the fill. So here for the group 3, uh, I plotted output. We just have one borehole that has at the very shallow rockhead that has the group 3, and the others are the group 4 and group 5. So here we plotted together. This is the UHS uniform hazard spectrum at outcrop motion rock outcrop, and this is our median spectral that I used after I choose the 11 earthquake, so we can see the matching between them, and this is the response after 1D propagation into the soil, and this is the proposed spectral acceleration by Papin, okay, in his research in Tonman area, and I see this is almost match. Yes, there is some peaks here, but almost match. The design cannot just go like there and like this. No, we just take maybe a median of peaks to get this line. And for group 4 and RS group 5, I plotted them together. And we can see here, group 4, we already have design spectrum from Papin. It's called Arab 2012, okay, because Papin already is a consultant here in an Arab company. And then we can see here this is the US uniform hazard, and this is the median, the outcrop, and this is the result, the black colors, and this is the proposed one by Arab, but I change it this in this part. This is the part that this amplification related to the marine and soft soil. So in this orange color, we cannot consider this amplification. So I changed the group to this group and this equation, and also for the RS group 5, and this is the most area of the island is classified as a group 5, reclamation site group 5, and we can see the amplification, and we don't have any of proposed design spectra for this, so I proposed this equation for 1, 2, 3, 4, 5 intervals to use this in the design. And we can see the amplification is almost by 1.2. Okay. and this group can be considered for the reclamation island in Hong Kong. Finally, I will show the sun seismic hazard maps amplification based on the 1D site response. What happened? I just choose some period, maybe 5 periods, but I will just show here two period 0.05. It's called big ground acceleration map, and also at 1 second. So I just choose 2 period, but in my work I choose 8 period to show the maps like point 5, point 0, point 01, point 05, point 1, point 5, point 2, point 2, point 5, 1, 2, 4. I choose maybe 8 period to show the maps, but I will show you just two cases here. The first one, the point 01, is called big ground acceleration for design level. This is for before, and this is the comparison between the map for the. This is the site amplification means we just divide the spectral acceleration over the big ground acceleration. Okay, and get the amplification mean the spectral for the bedrock, spectral on the surface over the spectral acceleration at the bedrock at the same period. Okay, so here this is the site amplification map. Amplification means SA on the surface over SA on the bedrock. Okay, and we can see here the higher amplification. Why this higher amplification? Because in this map I plotted the data points, and here the contour, it's considered the small strain site period, to see if this affect the amplification or not, and how the amplification has influenced by the small strain side period. We can see here it's the higher value here too, because here it's almost match. It's close to, because here maybe you can see it's a very short period, and here we have a very short period for BGA, for so the biggest amplification here, and we can see we can compare between the equivalent linear and fully nonlinear. The same here we have the peak, but the peak here is not like 2, it's like 1.6. Okay, so we can see that the equivalent linear, especially at the short period or higher frequency, cannot capture the site response, and it is overestimated the amplification. But nonlinear has also amplification, but like 1.6 or 1.7, not 2. And also we can see the spatial variation also of the site amplification on the same site, related to the complexity of the geological condition and the variation in the marine and the subsurface soil layers. And here also for the 0.01 second, but here after reclamation. Here before, here after, we can see full peaks. This is 2, here is 1.6, 1.6. After reclamation, the amplification site is decreased due to some improvement in the soil. And here also I need to say that here I just consider fully consolidation for the marine deposit, finally, without taking the time of consolidation into account for our analysis. Okay, because the government here will do any improvement techniques to reach almost to 90% consolidation before construction. Okay. And here at longer period, 1 second, we can see the amplification here is 4. It's 4, that's mean that the amplification is more higher than at big ground acceleration at the longer period, due to the thickness of the marine. And we can see the variation almost the same. You can see the shape, and this is one of the validation of the result. The shape of the maps is almost the same. The change in color, because I made the color constant to see the difference. Here we have lower amplification, here we have higher amplification also in the equivalent linear, because at longer period also the equivalent linear analysis cannot capture the nonlinearity of the soft layer. And here for after reclamation, here almost 4, maybe here 4.5, here it's almost 4, but change it we can see before and after. This is the same, but the difference just in color. We can see here here, here it's like here, and also here it's like here. But the values of the amplification change. Here is higher than here. But also, yes, here it's higher, especially here we can see the side period is 1.5. That's mean that the soil profile here is weak. And here for the after reclamation, we can see change it. Here we have a higher amplification, we have lower amplification, but here becomes higher, okay? And this is the important to consider this because after reclamation, it doesn't mean that the amplification will be reduced at all. It based on the soil profile, it based on head level, based on many things, not just it's complex to just tell one constant statement, okay? It depends on the location and other parameters. Conclusion and future recommendation. The firstly, comprehensive 1D site response analysis. We did 638 runs using equivalent and nonlinear performed at the reclamation site. For equivalent linear, I used the Strata software published by University of Austin, Rathje and Hare Group in Texas. And for nonlinear, I used the Deep Soil published by Professor Yusuf Hashash and his group. And amplification factor confirmed the importance of rockhead depth as deeper head, higher spectral acceleration, and amplification factor at long period for both equivalent and nonlinear methods. The response difference between equivalent and nonlinear increases as the soil becomes softer due to the higher nonlinearity level. It recommended to use fully nonlinear approach to capture the real nonlinear behavior of soil. The amplification factor decreases for after reclamation case due to shear strength improvement, but not in all cases, and in all area of the island. Some, uh, not to maybe 10% of the island area change it to worse after reclamation due to the increase in the soil profile and due to that the small strain side period becomes longer. Design spectral group 4 has been modified because this is proposed in another site, not include the marine, modified to reclamation site group 4 to envelop the response for this site. A new design spectral acceleration for a soft soil profile called RS Group 5 has been proposed for such reclamation of artificial island. This research provides crucial data for informed decision making in the design and construction of structure on reclaimed land, and also the proposed design spectrum will contribute to improve seismic safety standard for Hong Kong. And finally, for future recommendation, could involve extending this analysis to consider the three complex geological three-dimensional complex geological model and take the three-dimensional effects because the rockhead has shape like this. So this shape for convenient and if we have some shape like down and ups, all of this can affect the site response. So we need to be more accurate. We need to move to the 3D and also take the liquefaction potential into our consideration in the future. And this is one of my model in the area in the 3D based on the data I have. And this is carried out by Leapfrog software. And maybe after some fine tuning for this 3D geological model, I can take the output of this to be the input file in the spec FEM regional scale site response analysis. And this is the three published paper. This first one in Milan, World Conference Earthquake Engineering last year. This was the preliminary, not this work. This is before my presentation. I did some preliminary to see if I need to do this research or not. And this is in November 2024. This related this. Our presentation today is based on this paper, and inshallah in August, I will present this paper. This paper almost for design level, And this paper almost for maximum consider earthquake. That's mean for the 2% probability of exceedance in 50 years earthquakes. Thank you for your attention. And anyone has any question, I am with you.
Thank you very much. Impressive work. You can share, if you don't mind, like your papers with the audience. It would be a great opportunity for them. Any question, please, like send it directly to Dr. Khaled, because we need to move to the next lecture, because we're running out of the time. I appreciate your attendance, Khaled. Impressive work, mashallah alik.
Thank you.
Dr. Muhammad Hassan, are you here?
Yes.
That's great. Can you share your screen, please?
Yes, I can.